So this talk I will be talking about a work which we have done on understanding the non-monsoon. Basically we are talking about non-monsoon means winter time and early spring precipitation response in the Karakoram and Hindu Kush Himalayas to climate change. And these are my collaborators, Dr. Sabin, who did all modern experiments, and my other co-authors. Basically, as we have seen that the HKH region gets precipitation both from the summer monsoon and the summer monsoon, as well as the winter time disturbances, what are known as the western disturbances during the winter. And this precipitation is very important for the Himalayan cryosphere. And the question is, in a changing with climate change and with global warming, how it is going to affect the precipitation patterns in this region. And this morning we heard some talks describing that the precipitation, the snowfall in some of the areas in the northwest Himalayas have actually increased in the last 10 years or so. So this is a very important question because it's going to affect and if you look at the seasonal distribution, the central Himalayas get most of the rain during the May to October months, basically the summer monsoon season, whereas the northwestern part of the Himalayas get substantial rain in the winter time in the form of the western disturbances. And so the global mean temperatures increasing by about nearly 0.9 degrees during the last century. Even the Himalayan region has also warmed at a very similar rate, and these are also recorded in the tree ring width growth. This by Hemant Borgaonkar in the western Himalayas. So the question is how it is going to affect the precipitation pattern. There is a paper by Bhutiani et al. Describing the observed at various locations in the northwest Himalayas, how the temperatures have increased. And the warmest, the maximum increase is during the winter time, where the stations are as much as 1.6 degrees during the last century. And there is another important feature that we see is what is known as the elevation dependency of the temperature trends. So when you go to higher elevations, the rate of warming is much higher as compared to the lower elevations, especially more than 2,000 meters above the sea level. The warming rate is much higher. So the physical mechanism for this is not fully understood, and this is reported by various studies. So the question is, if this is going to happen, what are the large-scale influences on the atmospheric circulation, whether it will influence the western disturbance activity, and so on, how it will affect the precipitation in basically the winter time precipitation in the Karakoram and northwest Himalayas. And already some studies are showing that in this region, the glacial mass, this is by Bolch and Anil Kulkarni is also involved. He says that some of the glacier mass has actually increased. There is a positive mass balance, and is also reported in another study by Gardi et al. Indicating a slight mass gain in the Karakoram glaciers. There is another paper in 2014 by Kapnick et al. Who used the GFDL high resolution climate model, and they noted that the snowfall in the Karakoram Himalayas is less sensitive to warming because of a unique seasonal cycle, and they noted that winter time precipitation in the RCP 8.5 scenario, actually at the end of the century, actually it increases. The snowfall in that region is actually increasing, and although the mechanism is not well understood. So we wanted to study this problem, what is really happening to the western disturbances. So we made some very high resolution climate change simulations, and the western disturbances are basically synoptic disturbance coming from the Mediterranean region during the winter and early spring. So we are going from the period January to April, and you can see the ITCZ is close to the equator and south of the equator, and these are some of the storm tracks. And these disturbances are basically these are what are known as the baroclinic systems, which get their energy from the mid-latitude and the subtropical westerlies, and And when so these were propagating disturbances when they travel eastward and when they encounter the Himalayan region. This was a famous work by Pisharati and Desai. The winds start packing up, basically the northerly winds, when they interact with this orography. And this is a very important mechanism for giving very stationary. It basically anchors these troughs in on the windward side of the Himalayas, and it's a very important mechanism for producing precipitation. You can see on the downward side there is more kind of diffluent flow. And when we look at the mean precipitation itself during the January to April months, you don't see any long-term trend as such. But when we look at the heavy precipitation events, this is the map of precipitation exceeding the 90th percentile for the DGFM season. This from the Aphrodite data. We see that there are areas where there is a significant, these are statistically significant trends. And this is for the period from 1951 onwards up to 2007. And in more recent periods, we have included the TRIM precipitation from the TRIM satellite to see a similar increasing trend. And in an earlier study by one of my students, Madhura et al., we had seen that we had an index of the western disturbances. We had seen that the amplitude of the western disturbances, there was an increasing trend in the amplitude variations of the western disturbances. So the question is whether this is forced by anthropogenic changes or is it a natural variability. So to address this problem, we had this very high resolution, the global model with a very high resolution setup. It's a telescopically zoomed setup with about 35-kilometer grid. And as you go away from this region, it gets coarser. And so because we wanted to have, because this phenomena is the western disturbances are coming from faraway place, we need a global framework. But at the same time, to capture some of the changes in the precipitation in this region, you need a high resolution zooming. So we use this configuration. We made 3 climate change experiments. One is the historical run going from 1886 to 2005. It's all part of our CMIP-5 runs. And this includes both the natural forcings like the irradiance changes and the volcanoes, as well as greenhouse gases like carbon dioxide, aerosol, land use change. We have varied them through the 20th century following the CMIP-5 norms. And then we had a historical run where all the GHG and the aerosol and land use values were fixed to the pre-industrial values of 1886. So if you can compare these 2 runs, you will be able to see to what extent the anthropogenic influence is influencing the climate in that region. And we also made a future projection following one of a moderate scenarios known as 4.5 going into the future. I'll not go into the details. So this is the climatological mean distribution from the era interim for about last 30-35 years or so. You can see the mean winds, the subtropical westerlies. The model also has a strong westerly wind, but the westerlies are much more stronger in the model. And also when you look at the precipitation in the observations, this is the Aphrodite and this is the model. Model rainfall is much more enhanced and stronger winds. And the temperatures are cooler, somewhat cooler in the more cooler in the model compared to observations, mean feet. And we also had 3 regions: the Western Himalaya, Central Himalaya, and the Eastern Himalaya. And these are the seasonal cycle of rainfall and temperature in the observations and model. So you can see that roughly the model captures the seasonal cycle well, both in the temperature, although there is a kind of cold bias in the model and also a wet bias in precipitation. And we also compared the solid and liquid precipitation. So winter time, most of the precipitation in the Western Himalaya is in the form of snow, frozen precipitation. We also looked at from the daily zonal winds. We did a power spectrum of the 200 hectopascal winds over a broad region. This is from the era interim. You can see the high frequency synoptic variability going from 4 to 7.3 days or so. The model, it captures the synoptic scale, but maybe slightly longer, going up to 8.3 days. So basically I want to say that the model and so coming to the point, we looked at the difference in the last for the period 51 to 2005, the difference between the historical and the natural run. So when we look at the surface temperature, you see a big warming. These are all statistically significant warming trends. This is the magnitude of change in the temperature. Interestingly, the precipitation in this region increases, and in particular when you look at snowfall, the snowfall in the Karakoram Himalayas are actually showing an increase. This is for the historical period, and rainfall also there is an increase. We do see a decrease in snowfall in the central and the eastern Himalayas, but the Karakoram region there is a very clear increase in the snowfall. So we were intrigued by this. When we see a warming in the increased surface temperature warming, it is accompanied by increase in the snowfall activity. So how to explain this? And we also looked at the spatial map of trend in precipitation extremes exceeding the 90th percentile. Clearly much of the precipitation is associated with increase in the heavy precipitation events, and this is also projected to continue into the future, although there is a slight decrease because of some increased variability in this. And so we don't see in the historical natural run, you don't see an increasing trend in the heavy precipitation, whereas you see clearly in the historical run and also into the future, indicating that this trend in the precipitation extremes and is influenced by anthropogenic effect of due to greenhouse gases largely. And we also looked at an index of western disturbance amplitude variations, which we constructed from the geopotential data. This is from the era 40, which goes from 1958 onwards up to 2002, and then in the post-satellite period, the era interim data from 1979 onwards. Both of them show an upward trend in the amplitude variations of the western disturbances. Now, when you do the same analysis of the western disturbance amplitude variations from the historical and the natural runs, we see a clear increasing trend in the historical run and also into the future. And of course, we see some intraannual variations superposed on that. So how do you explain this? So we wanted to have a mechanistic model to explain these amplitude variations of this western disturbance, how it can happen. So as I mentioned earlier, there was this elevation dependence warming of the climate signal. So when you go to, this is what we are thinking. So when you go to higher elevations, the rate of warming is more so in the Tibetan plateau. So this is the change in the temperature between the historical and natural surface temperature. We have shown only this difference only for elevations more than 3 kilometer height. You can see that very strong warming in these regions, high elevation regions. So what our understanding, once you have this type of elevated warming signal due to climate change, it adjusts the atmospheric response to this warming adjusts in such a way that you have a kind of anticyclone, because you have a warmer column, air column in these high elevated regions. You get a very strong anticyclonic high pressure region and with an anticyclone. And in the areas with lesser warming, you in fact have because you have a kind of zonal gradient, you have a kind of opposite type of flow. So these are changes in the mean flow circulation in response to a very strong climate forcing that you are putting. So you are basically setting up an east-west gradient in the geopotential and the circulation field, and such a change in the basic field which you are introducing because of this elevated warming signal allows formation of these very deep troughs, meridionally deep troughs, and you can see this acceleration of these southerlies and very deep northerlies which is behind. And so we believe that this elevated warming signal is kind of setting up a large scale circulation pattern. Of course, this pattern is also influenced by atmospheric variability, internal dynamics, but the manner of forcing in which you have more warming at the high elevation region also creates such an environment. And this is what is apparently introducing this increased variability of western disturbances. So in summary, what I want to say is we are seeing that how the winter to early spring precipitation is going to change in the western Himalayas, and recent observations in the recent decades, at least in some stations, they show an increasing frequency of this heavy precipitation events, and we think that this is linked to human-induced climate change, and these are basically changes in the subtropical winds and the mid-tropospheric temperature gradients that create this kind of situation. And in the future also, and when this happens, we can expect snowfall enhancements in the higher elevations of the HKH due to the increased WD activity. So with this, I want to end my talk. Thank you.